Hello there and welcome back. What we're going to do in this video is investigate the theory behind simple harmonic motion. And what I'm going to do is set this in motion here in a moment here. So what we're going to do is model this point going around the circle counterclockwise. And what we're going to do is monitor the way that the X and Y coordinates change. So I'm going to press the play button over here off the screen. And as you can see, as the point rotates around the circle, notice how the x coordinate of the point is oscillating back and forth, and the y coordinate of the point is oscillating back and forth. And this, the y coordinate specifically, models the mass being tied to a spring and the spring bouncing back and forth between two positions. And this is basically the idea behind simple harmonic motion. Now, what's happening also at the same time is that there is a constant angular speed happening here. So remember from angular motion that omega was the symbol for angular speed. So this has a constant angular speed going around the circle. If I were to, I'm going to start this over again. If I were to speed this up, notice how the oscillation would get faster. Let me hit play here. So that's a higher angular speed. Okay, so that means the higher the angular speed naturally causes a change in the period of motion. In other words, the time it takes to make one complete cycle. So this is why omega, the angular speed from angular speed back when we talked about linear speed and angular speed, has a lot to do with simple harmonic motion. Okay, so that motion, I'm just going to go back to the normal again. That motion where we have a quantity bouncing back and forth between a high and a low is simple harmonic motion. Okay, and that is your demonstration.